Somewhere in a child's career at the primary level, he or she should have come in contact with electricity and magnetism, learned about the field lines in a magnet, and learned about how to make a complete circuit. We're going to break this section of electricity and magnetism down into three parts: static electricity, current electricity, and then magnetism. And there's interrelationships between all three, and I like to teach it in that order. The first thing we're going to look at is static electricity. To understand static electricity, we have to understand some very basic concepts in chemistry. And back in the chemistry section, in the matter section, we learned about atoms being made of three particles: protons, neutrons, and electrons. Two of these particles have charges on them, electrical charges. And this is what electricity is all about, electrical charges, and in particular the electrons, because we can't mess with those protons. They're in the nucleus, and only an atom smasher can get them out of there. But the electrons can be rubbed on and off things, and in some materials the electrons move readily. We're first going to look at rubbing electrons on and off things. This is static electricity. Now there's two unifying concepts that you should pound in when your students study this. First, that all matter, whether a solid, liquid, or gas, being made of atoms, must have an electrical nature about it. And we can test this to see if it's true. And second, that static electricity is much like magnetism, where unlike particles attract each other and like particles repel. But it's not magnetism, and you have to keep reminding them this. It's an entirely different force of its own. Now there's a couple ways to study static electricity and a number of interesting experiments. There's the sedate way, and then there's the wild way. Let's take a look at both of them. First, the sedate way. Your students can use a plastic ruler and a piece of wool. You want them to rub it vigorously. What they're doing is putting extra minus charges on the ruler. More minuses than pluses, so it's getting charges built up on it. If this is minus, you should be able to bring it near any type of matter, and it should either attract or repel if there's an electrical nature surrounding the matter. Now you have to use light materials like tiny bits of aluminum foil, little bits of paper, Rice Krispies, sesame seeds, iron filings. Test lots of things so the students realize that yes, every material seems to have an electrical nature associated with it. Here's how we can do this. Rub it very quickly and then bring it near an object. We're going to take a look at this aluminum foil. What do we notice happen? Well, first the foil flies toward the ruler, some pieces stick, and other pieces repel and fly away. What's happening? Well, think of the electrons in the foil. As the ruler gets close to them, they try and get as far away as they can, so they move to the other end of the foil. What's left are the plus charges, and they attract the ruler. The piece of foil goes flying toward the ruler. Some pieces stick with the plus to the minus, and other pieces pick up the minus charges from the ruler. They transfer into that foil, and now the foil is negative, and so is the ruler, and they want to repel, so it goes flying away. Now it's difficult to test gases with this type of equipment, but we can test liquids. Turn on a water faucet so you have a narrow, smooth stream of water, and then hold your charged ruler near the stream. It'll bend the stream and attract the water. And if you can't find wool easily, you can substitute paper towels. Works almost as well. Now, another thing you can do that's really kind of fun is get a little plastic box, a narrow one, and put some very tiny pieces of tissue paper inside. As you rub the top of the plastic box with your piece of wool, it'll alternately charge up and discharge these little pieces of tissue paper, and they'll go bouncing up and down. Now I think we're ready for the wild way. And this time you're going to have students all around your room rubbing their hair with balloons. I have found that rather than rubbing a balloon with wool, it works better on hair. So tell your students the day before to wash their hair. The best kind of hair is dry, clean hair. And sometimes long hair, medium length blonde hair seems to work good. What we're going to do is give our student groups a balloon each. They rub their hair with it, and then they test the materials just like they would with the ruler. But one of the first things they'll notice is that after you rub your hair, this gets negative, and your head has lost a lot of its negative charges. They've all rubbed off your head onto the balloon, so your head is really positive. And what's going to happen to the hair that's positive and the balloon that's negative? Well, you'll see something like this. Students can then rub their hair with the balloon and test different objects, and this balloon gets a lot more charges on it than that ruler would. Look at what happens when we take a look at Rice Krispies. I can hear the oohs and ahs now as your students do this experiment. Look at what happens when you bring your finger close to one of these little Rice Krispies. It flies away. See if a student can explain why these particles are flying away. And when you're doing experiments with static electricity, a cold, dry day will work best. The reasoning is that moist air conducts electricity and the charges will leak off the balloon. You might also try and see what size of an object, how big of an object you can manipulate under this balloon. I've managed to get small corks to dance around even. Now we're ready for one more experiment. This time you just need Scotch tape. Tape a piece about 6 inches long on the tabletop and then pull it off the table very quickly. It'll be charged up. Look what it does when it's brought close to your body. It's attracted and sticks to your hand. So there's some kind of attractive force between a piece of Scotch tape even and a human being. This suggests that we're also made out of these charged particles. What would happen if I pulled 2 pieces of tape off the table together? This is a prediction question. What do you think will happen when I hold them close together? Well, they repel, they push apart because they have the exact same charges on them. We've demonstrated a number of things here. First, that all materials, we're starting to see this, all materials are made of electrical charges. Everything we test with the balloon seems to bounce around and attracts and repels. The second thing is that like charges repel, as we saw in the tape, and unlike charges attract. Now we'll go on and take a look at current electricity. If your life is anything like mine, you probably agree with me that there's always something electrical going on the blink, whether it's a washing machine or a hair dryer or a television or a car horn. And I can't guarantee you're going to be servicing televisions by the time you learn this segment on electricity. But many times you can fix an electrical appliance because it has just a minor problem. It's usually in the circuit that gets the electricity to the appliance. It might be a fuse or a frayed wire. This is why it's very important that students have hands-on experiences with the electrical equipment, that they have the ability to make these complete circuits and learn about them. There's the hidden benefit in studying electricity besides it being very practical, and that hidden benefit is learning logic. Electricity is an excellent vehicle for learning logic and making simple deductions. We're going to start to study electricity by taking a look at batteries. There are some concepts in science that are somewhat difficult, but can be very easily explained using an analogy. In this case, it's very easy to explain how batteries work using containers of water. First, let's look at these 2 containers. Look at the height of the liquid. This is what we're going to call the potential difference. How much higher is the surface than the bottom? Well, in these 2 containers, the height is the same. In a battery, it's measured in volts. How much higher is one point to the other? The other thing we want to look at in these 2 containers is which one holds more liquid, the large one or the small one. This is the capacity. How much liquid can flow from this container? Let's think of a ramp that's sitting up at 1.5 volts. If we poured this liquid down the ramp, how much current could we get flowing down as compared to pouring this liquid down the ramp? We start to see the relationship to current carrying capacity. Then what would happen if we took 2 of these big batteries and set one on top of the other, and our ramp is not this high now, but twice this height? Would the current go faster when I poured it down the ramp? There's a very good lesson here about the greater the voltage, the more current. You're starting to see this whole picture of batteries. So we have voltage and we have current. 2 important characteristics. And we can now switch to real batteries and take a look at them. These 2 batteries are both 1.5 volts. Which one would turn a light bulb on for a longer period of time? The answer, of course, is the bigger one, the one with more capacity. Now, you may have a problem here looking at them. They're not the same height, and there's where our analogy kind of has a flaw in it. but you have to explain this to the students, is that voltage is not really a linear dimension. It's not actually measuring the height of a battery. It's measuring the power, the voltage difference. And a good way to do this is go back to the static electric balloon experiments. If we shake it a little bit on our hair, we get a little charge on it. If we rub it a lot, we get a lot of charge. And the voltage difference between us and the balloon can get greater, and that's what we're measuring, the voltage difference between these 2 points. Now, as we learn about batteries, we can go on and see how batteries come together to make additive voltages, and how we get little packs of batteries like this that are really all stacked one on top of the other. Let's look at some problems. First, 2 batteries stacked end on end. We know the voltages add together and we get a total of 3 volts. Think of this capacity being poured down a ramp that's 3 volts high. The current would flow faster, and as a result the battery would drain quicker. Let's think now of these same 2 batteries now side by side. In this case, the voltage difference between the top and the bottom point is only 1.5 volts, but it has now twice the capacity. It can pour current down a ramp that's 1.5 volts high with a slower speed, so it'll last longer. And how about this configuration? Your first guess might be 1.5 volts, but a closer inspection will show that these batteries are really stacked end on end to give you 6 volts. Now that you understand sources of electricity, let's look at the other side, what we call the load, the resistance, things that push back against this flowing current. If we had our ramp up here and we had little objects sitting on the ramp, as the liquid flowed down the ramp, this would kind of disrupt the flow. It would slow it down, and the force of the material hitting the objects would heat the objects up. Do you think the objects would get hotter if we poured the current down from a 1.5 volt ramp compared to a 3 volt ramp? The current will flow faster down the 3 volt ramp and heat up the wire more. This is what happens when we have an electric light bulb. We narrow the wire down, and in this case we're narrowing down the channel. When the channel gets smaller, the liquid gets knocked around more and there's more friction involved, so things start to heat up. And this little tiny filament inside this bulb starts to get hotter and hotter, and eventually gets so hot it glows. If we pour too much current through this bulb, in other words, if we take it on a higher ramp than it's supposed to be run at, and we pour a lot of liquid down through that bulb at a very fast rate, then that little filament will get so hot it'll burst. This analogy of relating water to electricity is very good for explaining voltage, current, and resistance. Now we're ready for an exercise in logic as we investigate circuits. If you want your batteries to make it through the school year, I recommend you get batteries that have enough capacity. At least use the D size cell. This is the 1.5 volt size. And a light bulb to use if you're working with this type of battery is the GE14. It's rated at 2.5 volts. When it's hooked up to one cell, it'll burn dimly. When it's hooked up to 2 in series at 3 volts, it'll burn brightly. Let's start by reviewing the simplest complete circuit. 1 battery, 2 wires, and 1 bulb. And have your students work in as small a group as possible. Their task is to make the bulb light up. Once everybody in the class can do that, then we'll go on and challenge them to make the same bulb light up, but this time with only 1 wire. And many students don't know that this casing is really one of the terminals, so sometimes they need a little help in this one. Then we want to go on and make hypotheses, guesses. What would happen if we used 2 batteries and stacked one on top of the other? And we think back on this ramp theory where we're pouring the water down and now we've raised the ramp higher. What do we expect will happen to the brilliancy of the light bulb as more current is going through it? And then have them try that experiment, and this time have 2 groups come together so they now have 2 batteries between them. Give each group a battery holder, and this one has a red and a black wire coming out. Red is plus and black is minus. Have the students look it over and see how the batteries are interconnected, and remind them that the electrons flow from minus to plus. Also, each group should have 2 bulbs, and we're going to start investigating what happens with 2 batteries and 2 bulbs next. But before we do that, it's really cumbersome to try and hold wires on bulbs. So you want to have either commercial sockets like you see here, or your students can put together their own. Here's how to do it. Start with a piece of wood, 3 thumbtacks, a bulb, and some copper wire. 20 or 22 gauge works well. After you've scraped the varnish off the wire with sandpaper, wrap it around the bulb. Push 1 tack into the wood for one terminal, then secure the bulb with 2 more thumbtacks. This will also be the other terminal. For the wire that you hand out, use 18 gauge stranded wire if you can get it, and you should strip off the insulation before you hand it out. To easily get the insulation off, all you have to do is burn the end of it with a lighter and then just pull it off with a pair of pliers. Now we want to see what we can do with our 2 bulbs and our 2 batteries. How can we hook up the 2 bulbs in 2 different arrays and make guesses about what we might expect before we try the experiment? Well, there's 2 types of hookups. There's the series and the parallel. Let's first look at what the series circuit would look like. In a series circuit, we have the electricity flowing first through one bulb and then through the other before it gets back around. Let's go back to our analogy with the ramp. This time the ramp is up 3 volts. We have the current flowing down the ramp, but we have 2 pieces of resistance in the middle of the ramp. This is going to slow down the current. With the current going slower, would we expect the light bulbs to be bright? Would we expect them to be as bright as if there was just one bulb, one resistance here? The answer, of course, is no. And when the students hook up the circuit, they'll see that the bulbs are only half as bright. They seem to be as bright as they were when they only had 1 battery. The second type of circuit is a parallel circuit. And here we're going to substitute our picture of a battery for the international symbol of a battery. The long line is always the plus end. Let's trace the current through this circuit. The first light bulb feels like it's the only resistance in the line, and the current goes directly from the battery through the light bulb and back to the battery. What about the second light bulb? It feels the same way, so it gets current too. Both of these light bulbs will be lit up brightly because there's no other resistance in the line as far as they're concerned except their own. It's like 2 ramps with the current flowing down both at once. But what about this poor battery? If it's taking all this current to power 2 light bulbs, it's really taking twice as much, and it's going to wear the batteries down sooner. What would happen if we removed the second bulb and replaced it with a straight wire? Now all the electricity wants to go through the straight wire, and none of it wants to go through that first light bulb. So we have what's called a short circuit. The first bulb will not light. Remind your students that this is not a good setup to have because it takes much of the current from the battery in a very short period of time. Now we want to investigate the operation of a switch. A switch opens the circuit, and as they've probably already learned, whenever there's a wire loose or a connection missing, their bulbs aren't going to light. This is making the circuit complete. How can we make simple switches? Well, here's an easy one your students can put together. We're using 2 thumbtacks this time and some foil from the bottom of a pie tin. When you press down on the top one, you close the circuit and make the electricity flow. Allow your students to experiment with a switch, and then ask them to design some circuits. Say they were given 1 battery pack of 3 volts, 2 bulbs, and 2 switches. How many different combinations of circuits could they design? And what will happen when one switch is turned on, or the other, or even both at the same time? Which bulbs will light up? Which circuits will be shorted? There's many different combinations using these materials. Here's just one possibility. What happens when both switches are closed? What happens when switch A is open and switch B is closed? And what happens when switch A is closed and switch B is open? The idea of resistance can sometimes be a difficult concept, especially when we don't always see light coming from the object that's resisting the current. This next experiment will test your students' understanding of resistance. What we're going to attempt to find out is how does pencil lead resist the flow of current? We need to set up the problem. How might we test it to see if electricity will pass through this pencil lead? Well, let your students come up with the idea if they can, and if they can't, here's the solution. We'll run the electricity through our test sample, the pencil graphite, and then we'll run it through a light bulb as an indicator, and then we'll leave the last 2 wires open so we can close it when we want to make our tests. We were using alligator clips in this experiment, and they're real handy to use. You can buy just the clips and make your own patch cords up, and a student can put these together for you. After your class has developed the circuit, give them the handout that tells them how to build the circuit and how to test the graphite in the pencil. Have them start by measuring a distance of about 10 centimeters or as long as the pencil is, and record the observations of the light bulb. Is it bright? Is it dim? Does it even come on? And then carefully move the alligator clips closer together. Go from 10 centimeters to 9 to 8 and so on, and continue to make observations concerning the brilliancy of the light bulb. If you find any students that are still having some difficulties with understanding this, walk by with a little patch cord and go from one alligator clip to the other. This will give them an interesting bit of information, that when you short circuit across the two alligator clips, the light bulb lights up real bright. Your students will conclude from these observations that graphite is a resistor. It slows down the flow of current, and the longer the piece of graphite, the more current it resists. We don't see light coming from the graphite because these resistors turn electricity into heat. Now's the time to start using the word resistor and even explain what one is. It's a common little gadget that we find in radios, and it's used to limit the flow of current. Inside this resistor is a tiny piece of carbon. The size of the carbon determines the amount of resistance that this resistor has. And these little colored bands can be converted into numbers which tell us the value of that resistance. Now it might be time to introduce the electrical symbol for resistance and rewrite our circuit on the blackboard with the little resistor sign in the circuit. Since we can vary the amount of resistance with the alligator clips, we can call this a variable resistor. The volume control on a radio or a television is a variable resistor. As we measure voltage in volts and current in amps, we measure resistance in ohms. Now we're ready for still another investigation. This time we'll remove the graphite and we'll substitute a light bulb in its place. We'll test the brilliancy of the two light bulbs burning together. We know there's twice the resistance of one light bulb in this circuit. Then we'll take the light bulb out and put the graphite back in. We'll now set the alligator clips just right so that the one bulb is lit up as bright as it did with the two bulbs. We can now determine that the distance between the alligator clips in the graphite is the same amount of resistance as one light bulb. Now let's go on and investigate parallel circuits, and this is really interesting. We have the electricity flowing not through one, but through two pieces of graphite in parallel. Would the light bulb be brighter or dimmer? Let's make a hypothesis before we connect the circuit up. And give your students plenty of time to make investigations with this circuit because there's so many different combinations. If they're still having problems understanding what's actually happening, give them a short piece of wire. With this, they can bypass different parts of the circuit. For example, one of the pencil leads, they can go right across the circuit. This will help them to understand which way the current is flowing. Now we're starting to get a total understanding of how current flows through circuits. With this information, we should be able to repair things. How would we go about troubleshooting something? Say your car horn is not working. What's the first thing you'd check? Well, I'd check the battery to see if I've got power. And one way to check a battery is to short two wires across it, and you're going to see one real bright spark, and you just want to touch it. You know you got power there. The next question, does the horn work? And you want to bypass all the wiring in the switch of the horn, so you want to go directly from the battery to the horn. If the battery will make the horn work, then you know that your problem lies somewhere in your wiring or in your switch behind your steering wheel, and it's just a matter of trying to hunt it down. But we're effectively troubleshooting. We're going through a systematic progression, digging into the circuit, looking at the components, taking them apart, and checking piece by piece. Now, we're going to take the information we've learned so far and this equipment that we have on hand and a couple other items like compasses, and we're now going to investigate magnetism. We'll begin the study of magnetism by suggesting to our students that when these electrons flow through wire, whenever we have a complete circuit, there's a magnetic force field surrounding it. How might we test that idea? Try and solicit some answers from the students once again. Maybe someone will remember from the primary grades that we can use a compass to detect a magnetic field. And then perhaps someone will come up with the idea of just run the wire over the top of the compass and see if the needle deflects, is attracted or repelled one way or the other. And when they do this, if they want to try this experiment, it will work, and it's very dramatic using just our regular 2-battery pack. But make sure that the wire and the needle are lined up together or it won't work. Next problem. Have your students make turns of wire around the compass and test to see how the number of turns affects the amount of deflection of the needle. By doing this, they should realize that if we make more electrons, more current, circle that compass, then we're going to produce a greater magnetic field. And your students can go on and make simple little current detectors by wrapping about 5 or 6 turns of this wire around the compass. But once again, make sure that the needle and the coil line up whenever you're making tests. Additional experiment with this is to see how varying the resistance in the circuit affects the amount of deflection. In other words, if we put one of our pencil leads in there and slowed the current down, what would happen to the deflection of the compass needle? And then a further experiment yet is to switch the battery around and have the current going the opposite direction. And now the needle deflects the other way. So where there was a north pole before, there's now a south pole. These are all very valuable experiences as we try and understand what magnetism really is. And we have to draw from the matter section when we talk about it. We have to talk about atoms with the electrons that are spinning around the outside. Some of the atoms may have the electrons going clockwise, and other atoms may have them going counterclockwise. So the magnetic fields from these two atoms will cancel each other out. To make a magnet then, we want to get the atoms lined up so the electrons are all going in the same direction. You can demonstrate this with an iron or steel bar. Hold it in the Earth's magnetic field in a north-south direction and pound very hard on the end of this bar about 10 times. You'll disrupt the atoms just a little bit, and when they come back to rest, there's a greater probability that they'll be lined up on the Earth's magnetic field. So you will have made a magnet. And if you want to disrupt this magnet, turn it east and west where there are no magnetic field lines and pound again, or hold it in the heat. That's 2 ways to disrupt a magnet. The next logical step is to have your students make electromagnets, and they can be made very easily by wrapping number 22 gauge copper wire around a nail. Students will experiment with the number of turns of wire and the voltage on the wire. They should find that the more electrons you can get to circle that nail, the stronger your electromagnet will be. Now all this time, we've talked about making a magnet by manipulating or running electric current through a wire. What about the other way around? What if we have a wire sitting still with no electricity in it and we rub a magnet past the wire? Can we now make an electric current? Well, this is the basis for our next investigation. We'll make the assumption that the current we generate is very, very small, so we need a very sensitive current detector. A light bulb just won't do it. In this case, we're going to use a compass with the wire wrapped around it, but we have to have many, many turns so that we can detect even the smallest amount of current. I've got about 40 turns of number 20 gauge wire here. In this case, remind the students to keep the needle pointed in line with the coil so that if there's any current, it'll deflect the needle one way or the other. And then make sure that you have at least 1 foot or 1.5 feet of wire between this coil over here and your detector, because the magnet is also sensitive to the compass and we want to isolate that. We don't want the compass needle turning because we're moving a magnet near it. We want to actually see it turn because of current that we generate. Now over on this side, we have a cardboard tube with about 30 turns of number 18 gauge wire. This experiment uses a lot of wire, but it's well worth it because there's a very important lesson here. As the students move the magnet in and out through the cardboard tube, they'll generate an electric current. If they add more turns to the coil, they'll increase the current. Or if they increase the power of the magnet, they'll also increase the current. Another interesting thing, if you turn it around and put the other pole in first, you'll see that the needle deflects in the opposite direction. This suggests that the current is now flowing in the opposite direction. The importance of this is that this is the theory by which all electric generators work. And almost all of our electricity today comes from spinning magnets inside coils of wire. To conclude our study on magnetism, we'll get the students involved in a full-blown experiment. First, be sure that they understand what these magnetic field lines look like. Get out the iron filings and look at the field lines again. And if you have the sun print paper, the solar graphic paper, it's excellent and a lot of fun. Once they've reviewed the field lines, we're ready for the experiment. We're going to use these ring magnets. North is on one side and south is on the other. Your students will discover how this invisible force field reaches out through space and how strong it is at different distances from the magnet. We're going to use different objects that weigh different amounts. We'll start with a very light object, like this pin you see here. It's tied onto a piece of thread. Behind it is a scale from 0 to 3 centimeters with each 1/10 of a centimeter listed. The magnet is taped to the bottom of the ruler and the 0 mark on the scale is lined up with the magnet. And right now there's more magnetic force pulling the pin up than there is gravitational force pulling the pin down. We know that the more mass an object has, the more gravitational force that pulls it down. So we'll experiment with different objects. We'll carefully pull down on the thread lower and lower and line up our eyes and read the number that the top of that pin is touching when finally it lets go from the magnetic field and falls. We'll record not only the distance in centimeters, but we'll weigh the pin and see how much it weighs. Test various objects like a small paper clip, a safety pin, and perhaps some nuts and bolts to get some heavy object. It all depends on how strong your magnet is. But leave some gaps in between, some weights that aren't tested. For example, this large paper clip. When the students graph the results, and we're going to graph distance on the lower axis and weight on the vertical axis, they'll come up with a very interesting curve. It'll look like this. When the students connect their dots together, they find that it's not a straight line, but rather a curved line. What does this mean? Well, looking closely, it means that the magnet is very powerful when we're very close to the magnet, but as we get further away, the power drops off very quickly. And what about this large paper clip? Well, first we'll weigh it. Mine weighed 1.8 grams. What distance would we expect the paper clip to fall off from the magnet? What we're doing is interpreting our graph for an unknown value. Well, we find 1.8 grams and go across until we hit the curve, and then we go down and read off the value. Then we'll test the paper clip to see how close our guess was. And there's another interesting thing you can do with this experiment. You can find out which group had the most powerful magnet. By comparing the graphs of each group, you should be able to figure that out. Now, we said that this is a full-blown lab experiment, so you should have your students write a lab report. The best way to set it up is to break it down into 3 parts. Part 1 is what I did, Part 2 is what happened, and Part 3 is what I found out. In Part 1, they list everything that they did and make a drawing if necessary and include the materials, but be brief. In Part 2, we want the results, any of their observations and all of the data they collected, and they may put the data down in a table. And finally, Part 3 is the conclusion. That's the interpretation of the data. What did they find out by doing this experiment? In conducting investigations like this, the students are not only learning about magnetism, but they're seeing the interrelationship between different science topics, and they're seeing the link between science and other content areas like mathematics and language arts. And who would ever believe that we'd be using a balance in an experiment with magnetism? As you can see, the balance is probably the most valuable, versatile piece of physical science equipment you can own. Put that as a high priority on your list. As you review the information on these tapes, you realize that you are now the science expert. Don't hesitate to try new science experiments on your own. And for continued professional growth, I encourage each of you to join the National Science Teachers Association. Along with your membership, you'll receive an excellent publication entitled Science in Children. It's packed full of new experiments and ideas that you can use in your program. And if there's a regional or national convention in your area, by all means attend. It's a gathering of teachers just like you, sharing new ideas and tips in science education. Remember, for the success of quality science instruction, each of us must do our part.